Hi, this is Shelley Physics lab measurement segment on the inverse square law of a magnetic field. Now, the inverse square law can apply to many things, including the light intensity of a light bulb, of course, a magnetic field as we're going to see here today, but also electric fields and many other things like that, gravitational fields as well. So this inverse square law transcends a lot of different types of forces. All the forces have a leaning towards an application of the inverse square law. So exactly what is it? That's what we're about to learn here today. We're going to be using a magnet with a meter stick, and what we're really trying to investigate here is how does distance affect the intensity of a magnetic field? You might know that if you put two magnets close together, they either stick or really attract toward one another, or they have a strong repelling force. But if you pull them further away, that intensity doesn't seem to be as much. So we know that distance has an effect on the intensity of a magnetic field. So we're going to call this magnet over here the source. That is the north side and the south side. It's a bar magnet. And I'm using this wooden meter stick as a measuring device for distance. Now, what am I going to use for a magnetic field? I've got a vernier sensor here. It's called a vernier magnetic field sensor. You can rotate it like that. It reminds me of the little characters on A Bug's Life when they get the grasshopper's antenna. You fired! Okay, anyway, but I guess you have to be there. At the very tip of this is a little point. And so this measures the magnetic field that goes into this point. So there's a direction to magnetic field, as we're going to see here. If I put this magnetic field sensor right up to the magnet, real close to it, we're reading a -5 milliteslas. Now, Tesla is the standard unit for magnetic field in the SI system. Or, actually, that's a little redundant, in SI. And if I flip this around to the south side, we see a positive. All right, so that means there's a magnetic field coming out of this thing, kind of a positive direction away from it. When it was facing the north magnet, that would indicate there's a field line going into the sensor because it's a negative. So let's just make it for the rest of this measurement segment here. Let's use the south side so that we get some positive numbers out of it. As you saw, it's fairly strong, if a millitesla is a strong magnetic field. But what I'm going to do is just kind of show you here. I'm going to bring this, bend it a little bit here, make it a little easier for me. I'm going to bring this further and further out, and you'll see that way out here, we get sort of a weak 0.223 magnetic field, and no matter where I move it, it's not changing a whole lot. It's hanging around 0.2. Occasionally it skips to 0.18 or so, but mainly 0.22. It's staying there. I might actually have some kind of a magnetic effect going on here close to my board. Oh, maybe not. Okay, but there is this other thing that's close by me that is producing a non-zero magnetic field. And you'll see if the magnet doesn't really start to have an impact until right about here. So that's where we're going to mainly be taking a lot of our measurements. But way out here, it just seems to kind of be the same. What's going on with that? Well, here's another little test I can do. If I just start moving it around and pointing in different directions, we'll see that it does have a marked decrease. It's not around 0.2 anymore when I point in this other direction. And let's see, it's pointing towards me. Doesn't look like I have a very magnetic personality. Anyhow, so it does seem to be strongest if I point it sort of in this direction. Well, what's that seem like? If you're thinking a compass, that's exactly it. The Earth has its own magnetic field. So one of our lab procedures here is to zero this, and that's what I'm going to do here. I'm going to point this magnetic field sensor. It's going to right way out here at about the 50 centimeter mark. I'm pointing it toward the magnet here because that's the direction I'm going to keep it pointing. So we only want the magnet to have an effect on this magnetic field. So I'm going to say way out here, this is essentially 0. So I'm going to go ahead on my computer using Vernier Logger Pro software. I'm going to hit the 0 button, and there we go. Now, the thing about this 0 is it's going to kind of fluctuate. So wherever in this data collection segment, hopefully you have some paper here, and I'm going to call off certain distances. I'm going to go about 5 centimeter increments from 50 down to about 10, and then we're going to go at 1 centimeter increments. I think I might hit a 12 in there. We'll hit a 12. Okay, so once I call those out, you'll be able to see the magnetic field data up here. Now I recommend only marking data to the 10th. As you see, the 1000th place, and also we're going to see the 100th place. They dance around quite a bit. So let's call this 0 at this point, 0.0. All right, and ignore that 0.13, 0.04. It keeps on dancing around there. All right, so we have got our data out at 50 centimeters, and 0 is the reading there. Here's 45 centimeters. I'll let you mark it. Keep in mind we're only keeping the 1s and 10s place, so that would also be a 0 mark. There's 40, 35 centimeters. A lot's changing here so far, isn't it? There's 30, 25, 20. All right. So just a moment ago I said use the 10th place, but as you see, we're holding pretty steady in the 100th place. Why don't we call that a 0.03 milliteslas at 20 centimeters? Now let's go to 15. 0.067, somewhere in there. Let's call it a 0.07 milliteslas right there. Now let's try out 12. Okay, now we're getting something a little more constant. Taking around 0.13, 0.11, 0.15. So let's call it a 0.13 at that point at 12 centimeters. Let's go 10. Okay, good. What do you think? I'll let you pick that data point. Okay, I won't call one out. Then we're going to go 9 centimeters. 8 centimeters. You should be marking this data down. 7 centimeters. 6. 5. 4. 3 centimeters. 2. 1 centimeter. I gotta be careful with this data here. I'll show you why here in a second. Now if I try to cut that in half, you'll notice it doesn't change a whole lot. Okay, you see that? Nothing's changing there. And that's because on this sensor, it's got a maximum of 6.4 milliteslas. Now based on the calibration of this instrument, we may be a little bit off. We may be plus or minus even up to 0.5 of a millitesla. What we're really looking for here, though, is the pattern in the data. We're trying to find this trend and allow that data to tell us what's going on. So at 1, we had about 5.0 somewhere in there. If you back up the data or back up the video, it might have been a little bit different. But you'll notice when we get up to 1, it might be stopping somewhere there around 1, and it doesn't really get any higher than 5.4. So if you have any data 5.4 or greater, let's not include that in our data set, because what's happened is this thing's maxed out. We can't go any higher than 5.4. So we don't want to count that as a legitimate data point. Anything less than 5.4, let's count that data, okay? So now what I encourage you to do is plot this. You can use a free app from Vernier called Graphical Analysis, or you could use something like Sheets, Google Sheets, to make a data set and then plot it. I think that's a little more difficult. I do recommend Graphical Analysis. It's free. And I plot that data, put it in, and then apply a curve fit. And you're going to have several options. You can try out a linear fit, you can try a quadratic or power, but when it comes down to it, a good clue would be the title of this video. Try out that curve fit and see what the data shows. All right, so I hope this has been helpful, and intriguing and a little fun. Have a good one.